All right, welcome to the review video for the Unit 3 test. This is review. I hope to keep this short and sweet and know that the answers that we're going over in the simulations and different expectations for this are also at the end of each of these problems, with the goal being that you guys can work through these problems on your own as a way of practicing an in-class experience so that we are ready for the test in a few days. So let's read through these and then see what it's asking us. So the first question, a large manufacturer of batteries knows that historically 10% of its batteries come off the production line and they're defective, and the remaining 90% of the batteries come off the production line in working condition, which is what we want. Conduct a simulation to estimate how many batteries the company needs to pull off the production line in order to be sure of ending up with 10 working batteries. So we want simulate to get 10 working batteries. Okay, so how many simulations do we, or how many times do I have to go up until we get 10 working? Okay, so because we know that 10% are defective and 90% are working, we're going to use a single digit. Let's say assign, I don't know, the number 9 for a defective battery and 0 through 8 as a working battery. We're going to start with the first row. So start with first row of numbers and count the number of successes. Let's say 0 through 8. 9 we throw away. Stop when 10 working batteries are collected. So that's running through, count the number of times we get the digits 0 through 8, come up until you have 10 of these. We're going to repeat, repeated digits are allowed, I should say that, because these are just batteries. They're non-distinct, if you will. We can't tell the difference between one battery or the other. Count the number of digits the trial took to obtain 10 of the desired. So we want total number of tries. So let's run this out. I'm going to use red to highlight any failures. So we're looking for the number 9 to show up, and that would be a bad trial. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So once we stop here, it took, we're going to end right there. End trial 1. 11 needed for 10 okay batteries. And this is just describing, so I have a notation when I come to my conclusions at the end of how many times it took. So the next time, again, we're looking for the number 9. 8's good, go on's good, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can just end our trial right there. So we needed 10. 10 okay batteries. So that wasn't that bad. And then the last one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. End there. So in this trial, and in each of these, we can figure out the expected number of batteries it would take in our conclusion. So it required 11 batteries in trial 1, 10 in trials 2 and 3 to obtain 10 working batteries. The average of these is 31 divided by 3. Let me pull up a calculator really quickly. 10.33. So our estimate of the number of batteries required is 10.3 batteries. Our estimate for the number of batteries required is 10.3. Now, if we picked a different digit, let's say instead of 9, we picked 8 or 0, we might end up with different results. So that goes to the point of randomness and running a simulation. Next up, looking at samples and sampling techniques. A statistics teacher wants to know how students in her school feel about mathematics courses. She decides to administer a survey to a random sample of students taking a mathematics course. She has several sampling plans to choose from. Name the sampling strategy. There are 4 ranks of students taking the class: freshman, sophomore, junior, and senior. Randomly select 15 students. We should all recognize that that is stratified because we are going from layers. Her next strategy is randomly select 10 math class sections and survey each student in each of those sections. So that is our cluster design. Each student has a 9-digit number. Randomly choose 60 different 9-digit numbers and survey the students that correspond. So that is our simple random sample. And lastly, randomly select a number from 1 to 5. Use the class roster. Start at the number, then select every 5th student. So that is what we call a systematic sampling technique. If the teacher in question 1 simply surveyed all of her students, what kind of sampling would that be? Well, as we know, if you're just sampling the people in front of you, that would be a convenience sample, which would lead to under coverage is our word. This teacher may teach only higher level courses. I mean, I teach honors pre-calculus, calculus, and AP statistics. If it was me, I wouldn't get all of the students, which would mean lower performing students would be underrepresented. In that case, she'd probably conclude that students are more satisfied with math courses than they are if you didn't get the entire population. Okay, 3. Listed below are the names of 20 students who are juniors. Use the random numbers listed below to select 5 of them to be in your sample. Clearly explain your method. Okay, so first off, let's give everyone a 2-digit number. Let's say 01, 02, 03, 04, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So now we've got each of them assigned. So we're going to use the random numbers. So use random numbers. Sorry, I should say digits in groups of 2. Select the first 5 people in sample. Select the first 5 people. Of course, we're going to ignore 21 through 99 and ignore repeated numbers. We can't have the same person in the sample. So if we do this, we have 04, which is Deirdre. We have 02, which is Chris. That's 2. We have 85 doesn't count. 52 doesn't count. 59 doesn't count. 81 doesn't count. 18. 18 is Rob. 34 doesn't count. 7 is Eric. That's 4. 54 doesn't count. 60 doesn't count. 20 would be Stacy. So those are our 5 people randomly selected using this method. Name and describe the kind of bias that might be present if the statistics teacher decides that instead of randomly selecting students, not a good choice, to survey on how they feel about the course, she just asks the students to volunteer for their survey. And obviously, this is a voluntary response bias. The bias would probably be towards students who enjoy the course, and these students would rate the course more favorably, generally. Hey, respond if you want to answer the survey. Give me your feedback. The people that don't like the class generally hold that back when they're trying to communicate that, unless they know it's anonymous. How about if the teacher gives the survey during class one day? Well, this would be a convenience sample. This would only get the opinions of people that are in that class that day. And plus, the bias would probably be towards students who happen to attend class that day. They may enjoy the course more than students that are skipping or are at home or are virtual and don't get the same lesson. So this would be a convenience sample. Okay, we have 2 more pages, and both go towards experiments. We're identifying the different pieces, so the subjects, the factors, the levels, the treatments, whether the experiment is blind, single, or double blind, and the response variable, and then we're going to write out the design. So I'm going to read them, and then we're going to write out the different pieces. An article in a local newspaper reported that dogs kept as pets tend to be overweight. That is definitely true with our cat who is at home. Veterinarians say that diet and exercise will help these chubby dogs get in shape. The veterinarians proposed 2 different diets, Diet A and B, and 2 different exercise programs, Plan A and Plan B. Diet A, owners control the portions of dog food and dog treats. Diet B, a mixture of fresh vegetables with dog food and substitute regular dog treats with baby carrots. So Plan 1 is 3 30-minute walks a week. Plan 2 is 20-minute walks daily. 60 dog owners volunteer to take part in an experiment to help their chubby dogs lose weight. So the subjects in this case are 60 chubby puppies. The factors, here are the things that we are trying to measure. And we have diet, which comes in 2 plans. And we have exercise, which also comes in 2 plans. So if we have A and we have B, and then we have 1 and then 2, we have 4 different treatments if we have a combination of these. So 4 total treatments. Now, knowing how this study is designed, the owners themselves are having to both give the dog walks and they're also having to feed them. So at best, this design is a single blind. Since the owners know which diet and exercise plan their dogs are on, but the evaluators do not have to be given this information. So the people that end up with the results, they might not know who got what. So at best, we could call this a single blind experiment. With our response variable, the thing that we want to measure at the end is weight loss. So let's actually write out the design of this. We start off with our 60 dogs, and this is where we randomize. So what you could do is you could say they can either random assignment and random assignment. And we can say that we have diet A. So we want 30 dogs. And then we want diet B, which has 30 dogs. And then from there, we have exercise 1, and then exercise 2. And this would be 15 dogs and 15 dogs. Same thing. Exercise 1, exercise 2, and we have 15 dogs in each. Or you could skip the secondary bifurcation and just list out 4 total treatments. In the end, what we want to do is compare the results to see which dogs lost the most weight. So we can say compare results of weight loss. Moving on to the last example. So I'll read it, we'll go through each of the pieces, and then I will write down the solutions for this. So Max wants to start a farm to grow mussels. Not like flex mussels, but like things that you eat. He needs to determine the best environment for growing them. He's going to try 2 different amounts of salt in the water, it's called salinity, and 3 different water temperatures. For his experiment, he has 18 aquariums, must be nice, each with 20 mussels. He wants to see which environment produces the largest mussels. So first we need to identify the subjects. So it's not just the mussels themselves, but it's the 18 tanks of mussels, which I believe is around 360 mussels altogether. Let's say SSELS. SSELS. There you go. Identify the factors. So again, there are 2 factors, 2 things that he's changing. So it's the salinity and temperature. The levels that they have are, there are 3 levels for temperature, 3 levels, and 2 levels for salinity. So if we put these all together, there's going to be 6 total treatments. Let's spell correctly. So we either have high salinity or low salinity, and then we have our 3 temperatures. So let's say cold, medium, and hot. So we would have, I'm going to say high salinity, and low temp. High salinity, mid temp, and high salinity, high temp. And then we'd also have it repeat low salinity, low temp, low salinity, mid temp, and low salinity, high temp. 1, 2, 3, 4, 5, 6. Good. Identify the response variable. So at the end, how is he measuring these? He wants to see the size of the mussels because he wants to grow the largest ones. Describe an advantage to random assignment of treatment. So what a random assignment is we don't know what's going on with each and every one of these mussels. So we can't separate out other factors that are not controlled just by salt and temperature. So the advantage of random assignment is it would reduce the effect of confounding unseparable variables. Explain how replication can be used in the study. Since there's 6 treatments, each could be assigned to 3 tanks. So knowing that there's 18 tanks, we could do this on, say, since there are 6 treatments and 18 tanks, each could be assigned to 3 tanks. This allows for replication inside our study to verify or refute any of the findings that we have. Someone suggested that Max arrange the tanks so that 6 with the lowest temperature are on one end of the room and 6 with the highest temperature are at the other end of the room. Explain how this could introduce confounding into the experiment. Well, I just think about the location. There could be something about the location in the room that affects the growth of the muscle. Maybe sunlight, maybe where the air conditioner is positioned. There's a bunch of different factors that room placement might have. If this is the case, Max wouldn't be able to tell whether the location in the room or the treatment was responsible for the observed growth. So Max wouldn't be able to tell if it's the location or the treatment that had an effect. And why would it make sense to have a control group that did not get any of the treatments described above? Sorry, would it make sense? Okay. What would you be doing? Putting mussels into water at a temperature? So like if you used no salt, mussels would die. And it makes no sense to have no temperature. Like, what does that mean to control for temperature? Like if we're setting it low, medium, and high, obviously we have to have a low, medium, or high. And mussels are creatures of the sea. They need salt to live. So hopefully these examples walked you through some of the processes that we've learned from chapters 11 with simulations, chapter 12, which is sampling techniques, and chapter 13, which is experiments and observational studies. Good luck, Falcons.